So welcome to this lesson on redox equations, specification reference 3.5.3, and you'll have met redox equations before at AS and also at C3. So this is mostly a reminder, but we've got some added detail here for A2. Our lesson objective for this video lesson is to be able to apply the electron transfer model of redox to D-block elements. And in case you are not familiar with the electron transfer model, what we mean by that is, first of all, we assume, even in a covalently bonded compound, that electrons are being transferred to the most electronegative element in that compound. That's the one thing. So we're going to assume transfer, not sharing, of electrons. And the second thing about that electron transfer model is of course oxidation states and oxidation numbers, which are given by the electron transfers. And of course it also involves half equations. Okay, let's get on with it. Okay, what is a redox reaction? Let's just remind ourselves. And redox is just a combination of the term reduction and oxidation. And a gain of electrons is called reduction, and a loss of electrons is called oxidation. You'll remember oil rig as a mnemonic to help you remember which is which. Okay, so in a redox reaction they happen simultaneously, hence the term redox. And let's, while we're at it, just define the term oxidizing agent. Right? An oxidizing agent accepts electrons, but it gets reduced itself. Right, so it oxidizes something else and it gets reduced itself. Whereas a reducing agent donates electrons and gets oxidized. So it reduces something else but is oxidized itself. So let's have a look at an example here. A very simple reaction between sodium and chlorine. And as we know, we get sodium chloride. And what's happened is we have an electron from sodium has been transferred to the chlorine, to one of the chlorine atoms in the chlorine molecule. So let's just draw this like that. That electron that was in the outer shell of the sodium atom has been transferred to the chlorine atom to make it a chloride ion. So chlorine is the oxidizing agent because it's accepted an electron and has been reduced, whereas sodium is the reducing agent. It has donated an electron and has been oxidized itself. So a reminder about oxidation states, and the definition of an oxidation state is that it gives you the total number of electrons an element has either donated or accepted. And we have a bunch of rules for assigning oxidation states. So let's go through them with the aid of this table. So rule number one is that uncombined elements have an oxidation state of 0. So for example, if we had a sodium metal atom, the oxidation state would be 0. Rule number two is, and these rules are in no order at all, but anyway, the second rule that we're going to do is that elements bonded to identical atoms also have an oxidation state of 0. So for example, oxygen gas, oxygen is bonded to another oxygen atom, then they of course have an oxidation state of 0 as well. And thirdly, let's look at the oxidation state of a simple monatomic ion. And that oxidation number is the same as its charge. So if we stick with sodium, for example, a simple monatomic ion, let's say when it's in an aqueous solution, is the same as its charge. So it's going to have an oxidation state of +1. But in compound ions, the overall oxidation state is just the ion charge. Okay, so a compound ion might be something like a sulfate ion in sulfuric acid, SO4 2-, and the overall oxidation state is the charge on the ion, -2. Just notice here that when you write the charge on the ion, you write it as 2-, but when you write the oxidation state, you write -2. Okay, so let's think about a neutral compound now. So a neutral compound, such as, let's say, rust, so let's write in Fe2O3, that's a neutral compound, and so because it's neutral, its oxidation state is 0, and so neutral compounds are always 0. So getting towards the end, let's have a look at combined oxygen. So this is oxygen that has reacted with something, and combined oxygen, so let's use Na2O, for example, sodium oxide. So combined oxygen, so we're just dealing with the oxidation number of the oxygen in this compound, and the oxidation of combined oxygen, the oxidation number of combined oxygen is nearly always -2. It's the second most electronegative element in the periodic table. All right, so it gets its way nearly all the time. But the most electronegative element in the periodic table is fluorine. So whenever fluorine's involved, then it would take precedence and have its own preferred oxidation number, which would be -1 as it happens. So another rule is about combined hydrogen. So this is hydrogen once it's reacted. So let's say combined hydrogen in hydrogen chloride. So again, we're not looking at the hydrogen chloride molecule, we're just looking at the hydrogen in hydrogen chloride, and that combined hydrogen is nearly always +1, except for metal hydrides. So an example of a metal hydride might be sodium hydride or potassium hydride, for example, in which case that would be -1, right? But they are less common, and mostly combined hydrogen has an oxidation number of +1. And so once you've got those rules, then you can work out the oxidation state of an element in a compound. So let's do just that. Let's work out the oxidation state of chromium in this compound, chromium oxide. So let's write out the compound so that we can deal with it in detail. So we know from the rules on the previous slide that the whole compound is neutral. Okay, so it's going to have an oxidation state or an oxidation number of 0. That's what we know from one of the rules, and from another of the rules we know about the oxygen. Okay, so combined oxygen is what we have here, and combined oxygen, one oxygen is going to be -2, all right, but we've got 3 oxygens, so that's going to be -6. So the 3 oxygens are -6, and the only other thing in the compound is chromium, right? So the fact that we have 2 chromiums in there, they must account for the -6's to leave the whole compound as neutral, right? So if we write this down, so chromium 2 plus the oxidation state of oxygen 3 has got to be overall neutral. So this oxygen we know as -6, and the overall is 0. And so the chromium, from the chromium, both chromiums must be +6. So the chromiums combined, the two chromiums combined must be +6, because +6 plus -6 is 0. But we want an individual chromium. So we have to divide by 2 to get the oxidation number of an individual chromium atom. And 6 divided by 2 is +3. So the overall answer to the question is the oxidation number of chromium is +3. So in a chemical reaction, there are changes in oxidation states of the particles that are taking part. So I've got a quick diagram here that will help you understand changes in oxidation state. So let's say we start off at 0, and the oxidation number can go up to quite a lot. Let's say it can even go up to +7, and oxidation numbers can even go down. Let's say they can go down to -7. And that should cover all eventualities. So whenever an oxidation number is going in this direction, right? So it doesn't have to start from 0. You know, compounds, like in a displacement reaction, compounds are changing partners and making new compounds. So the oxidation numbers of the particles don't have to start at 0. So but when they go from a small number or a negative number to a more positive number or a less negative number, then they're doing that by loss of electrons. And you know that that is oxidation. And of course, it can happen in the other direction as well. Okay, so particles in a chemical reaction can start off with a high oxidation number when they've already lost lots of electrons, and they can gain electrons, all right, ending up with a more negative or a less positive oxidation number. So that is when they do that, when they gain electrons in a chemical reaction. And when they gain electrons, that of course is reduction. Okay, let's have a look at a real example. So let's have a look at the reaction between vanadium 5 oxide and sulfur dioxide. So let's write it out first. Vanadium 5 oxide plus sulfur dioxide reacts to give another version of vanadium oxide. I won't give its name because then I'll just give away the oxidation number with it. And sulfur trioxide. And what we want to do is we want to list out the oxidation state of vanadium throughout this reaction, and we also want to list out the oxidation state of sulfur. So let's have a look at vanadium in vanadium 5 oxide. So let me just, the name sort of gives it away, but let's work it out anyway. So the overall charge is going to be 0. The oxygen is -2 each. So the oxygen is going to be -10 overall. So that means the vanadium has to be +10, but there are 2 of them. So one vanadium is going to be +5. Okay, so we can write in 5 here as the, let's write in +5 in fact, as the oxidation state of vanadium in vanadium 5 oxide. And we find on the reactant side of the equation, let's also put the oxidation state of vanadium in here. So in the same way, in red, in the same way, this is still a neutral compound, but the oxygen, right, is still -2 each, but there's 4 of them, so that's -8 for the oxygen. So that means the vanadium's need to be plus 8, but there are 2 of them, so one vanadium is going to be plus 4. Okay, so let's write in plus 4 here for the oxidation state of vanadium, just make that clear. So that's vanadium done, and what you can see is that vanadium has gone from plus 5 to plus 4. And how does it do that? Well, it does that by gaining an electron. And so let's write that in as, if it's gained an electron, it's reduction. So let's write in reduction here. And now what we're going to do is we're going to do the same for sulfur. So in sulfur dioxide, the first reactant, the first sulfur product, sulfur dioxide. And what I'll do is I'll do this in red as well. Maybe blue. I'll do blue. Okay, so again we've got 0 overall, and that's a 0, not an O. Okay, so overall is 0, so oxygen is going to be minus 4. So sulfur has to be plus 4, and there's only one of them, so the sulfur is plus 4. So let's write out plus 4 underneath the sulfur of sulfur dioxide. And then lastly, let's also do the oxidation state of sulfur in sulfur trioxide. Okay, so again it's a neutral compound, right? So that's a 0 overall. The oxygen is going to be minus 6, which is 3 times minus 2, and so the sulfur is going to need to be plus 6, and again there's only one of them, so the sulfur is plus 6. So we can write in plus 6 here, and so you can see that the sulfur has gone from plus 4 to plus 6, and it's done that by losing 2 electrons. So if it's lost 2 electrons, then that is oxidation. Hopefully that's been clear, so we can move on now to half equations. So you'll be familiar with full balanced equations, but what are these half equations? Well, the half equations are just for a redox reaction where reduction and oxidation is happening simultaneously. You can write out 2 half equations, one for oxidation and one for reduction. So let's do just that. Let's consider metal ion rusting, i.e. reacting with oxygen in the air. So we might have a metal ion atom, and that's going to react with the oxygen, and what's going to happen to it is that it is going to turn into a metal ion, and it likes to make metal 3+ ions. And so in order to make the charges balance, right, because we've got overall 0 on the left hand side, so we need overall 0 on the right hand side as well, so we need to add 3 electrons. So it's lost those 3 electrons. All right, so if the iron atom has lost those 3 electrons when it becomes an iron ion, then it has been oxidized. Right, so let's just write the oxidation part of the redox reaction. So this is the oxidation half equation that we've written down already. And the other half of the equation involves oxygen. So the oxygen might be oxygen gas in the air. And oxygen gas, as oxygen atoms, as you know, they like to gain electrons, right? And there are 2 of them here. Each one wants to gain 2 electrons to give itself a full outer shell. There are 2 of them, so it's going to need to gain 4 electrons in order to make 2 oxygen 2- ions. So the oxygen has gained electrons, and that means it's reduction. It's been reduced, and this is a reduction reaction. So let's just write in reduction here. Alright, so these are the 2 half equations for the redox reaction that is iron rusting into iron oxide. One last thing to notice before we move on about these two half equations is that although each one balances independently, so the charges are balanced in both, there are 3 electrons being transferred in the oxidation reaction and 4 electrons being transferred in the reduction equation. So you couldn't actually combine those two as they stand to make a full redox equation. But that, of course, is the subject of our next slide. So let's have an example of combining two half equations to make a full redox equation. And let's use the example of zinc metal displacing silver ions from silver nitrate solution to form a solution of zinc ions and a deposit of silver metal. So just writing out the balanced equation, we're going to have some zinc metal and we're going to have some silver nitrate solution, and zinc's more reactive than silver, so it's going to displace the silver, and you're going to get some zinc nitrate. Nitrate's 1- charge, so you need 2 of them to balance the 2+ zinc ion, and you're going to have some solid silver precipitated out. And to balance it, of course, we need 2 silver nitrates and 2 silvers are deposited. Okay, so that's our balanced chemical equation. And first of all, let's consider the oxidation reaction. Okay, so what's being oxidized? So zinc is losing its electrons, so you've got the zinc metal, and it is turning into zinc ions, and they are 2+ ions, and they've given up their 2 electrons. Alright, so that's the oxidation part of the reaction, and the reduction part involves the silver. Silver's being displaced. Okay, so we're starting off with silver ions in solution. They are 1+. Let's just remember our aqueous sign for the silver ions. So the silver ions are accepting electrons, and that turns them into silver atoms, which are not soluble, and they drop out as silver metal. And so that's our reduction equation. And when we want to combine these into a full balanced redox equation, we can't do it yet, because you can see that here we have 2 electrons being given off, and here we only have 1 electron being accepted. So what we need to do is we need to multiply the second equation, in this case the reduction equation, by 2. So you would have 2 silver ions, and they would accept 2 electrons to give you 2 silver atoms. And once you've done that, then you can now add them together. And so when you add them together, the result is still 1 zinc, right? And it was solid, all right? And you had 2 silver ions, in solution. The electrons cancelled out, because one of them is on the reactant side and one of them is on the product side. And so what you get, that's what you started out with, and what you finish up with is 1 zinc 2+ ion and 2 silver atoms. That's solid, and that is our full redox equation. And it involved 2 steps. It involved writing out the 2 half equations, I suppose 3 steps, because the second step was we had to multiply 1 multiply 1 so that the electrons will cancel when combined, when the two equations are combined. And step 3 was combine the two half equations. And that's how we do it. Here's a trickier question for you, and it's of a difficulty consistent with one you might see in your exam. And we have acidified manganate 7 ions, right, and they're being reduced to manganese 2 plus ions by iron 2 plus ions. And the iron 2 plus ions are oxidized in that process to iron 3 plus ions. And we're required to write an equation for this reaction. So before we start, let's just write down a rule. I'm going to put it in the top corner here. There's 3 things that you can add, only 3 things. All right, so you can add water to your half equations when you want to balance the oxygen. So when you want to balance the oxygen, you can add water. All right, the second thing you're allowed to add is hydrogen ions, not hydrogen, hydrogen ions. And we do that when we want to balance the hydrogen. And the third thing we're allowed to add is electrons, and we saw that in the previous example. So they in fact are the 3 things we're allowed to add to a redox equation, or 2 half equations, nothing else. So let's start out by writing out the 2 half equations. That's the first step, write out the 2 half equations. Let's start with the easy one, iron. So we're given in the question that we have Fe2 plus ions. So we've got Fe2 plus ions, and they turn into Fe3 plus ions, giving up their electron like that. So that is our first half equation. That's the oxidation of Fe2 plus to Fe3 plus. Now the other half equation with the manganate ions is a bit more complicated, but let's start with the basic reaction we've got that's not going to balance yet. We're starting out with manganate ions as we're given in the question, and we're finishing up with manganese 2 plus ions. That's what we finish up with. And the first thing you'll notice, let me write it in blue, is that we have oxygen on one side and we have no oxygen on the other side. All right, so we have to balance that oxygen, and that's the first thing we're going to do. So we can leave the manganate ions alone, and we've still got our manganese 2 plus ions, but we're going to need to add water, right? Because that's what we add when we want to balance the oxygen. But look, we've got 4 oxygens on the left hand side, and so far we've only got 1 on the right hand side. So of course we need 4 water molecules, so that now the oxygen balances. So now the oxygen balances, that's okay so far, but of course what we've done is we've gone and made the hydrogen not balance. And so if we look at the hydrogens here on the right hand side, we see we've got 8 hydrogens in the 4 water molecules. So that's what we have to add to the left hand side. So we've still got our manganate ions, but this of course means that we have to add 8 H plus, right? 8 hydrogen ions, which is what we add when we want to balance the hydrogens. And there is a tip in the question. If you look back at the question at the top here, it says acidified manganate ions, and whenever a question says that, that's a pretty good hint that there's going to be hydrogen ions in the question somewhere. So now we've added, let's go back to balancing our half equation here. So we've got our manganate ion and our 8 hydrogen ions, and we've got our manganese 2 plus ion, and we've got our 4 water molecules. And if we have a look at this last half equation, we can see that although the manganese is balanced, the oxygen is balanced, and the hydrogen is balanced, the thing that is not balanced is the charges. On the left-hand side, we've got 8 plus from the 8 hydrogen ions, minus the 1 minus from the manganate ion. So that's 7 plus on that side. And we've only got 2 plus on the other side. So if we've got 7 plus on this side, let me just write that in another colour. If we've got plus 7 on this side and only plus 2 on this side, you can see that we need to reduce that plus 7 down to plus 2 to make the left hand side also plus 2. And we're going to do that by adding electrons. Okay, so if we've got a manganate ion and we've got 8 hydrogen ions, and we want to balance the charges, and we can only balance the charges by adding electrons, so we have to add the electrons to this side of the equation that is most positive, so we can bring that plus 7 down. So if we add 5 electrons, that plus 7 comes to plus 2. And then we still have our manganese 2 plus, and we still have our 4 H2O. So now if we check the charges, this is still plus 2 because we've not done anything to that. And this is now 8 plus minus the 1 minus on the manganate ion minus the 5 electrons that we've added, so that is also plus 2 now. So our manganese half equation now balances, and now what we would do is we would combine the two half equations to get the full redox equation. But before we do that, let's have a look back at our half equation for iron. And we're not going to be able to combine those as they are because we've got 1 electron in this iron half equation, that's oxidation half equation. So in order to enable the electrons to cancel, which is what we want, we're going to need to multiply this half equation by 5. So we would have 5 iron 2 plus ions, giving us 5 iron 3 plus ions and 5 electrons. So now we've done that, then we can combine this first half equation with this second half equation. Okay, so let's do that. First thing we do is we look at the electrons. We've got 5 electrons on the left hand side and we've got 5 electrons on the right hand side. So they're going to cancel. They cancel like that, and then we just add all of the other species. So we've got manganate iron. We've got 8 hydrogen ions, and we've got 5 Fe2 plus ions. Okay, and on the right hand side we have 1 manganese 2 plus, we've got our 4 water molecules, and we've got our 5 iron 3 plus ions. And that should be our balanced redox equation. But one last step to do is to check our charges on either side, because if the charges don't balance, we've done something wrong. So let's check our charges. Go back to green. So on this side, the manganate is going to be -1, and the 8 hydrogens are going to be 8 positive, +8, let's call it. And then we've got 5 of these 2 plus ions, so that's 10 plus altogether, +10 altogether. And so that is going to add up to 17 on this side. And then on the other side, we have 2 plus 2 for the manganate. The water is a neutral molecule, and for the iron 3 plus ions, we've got 5 times 3 plus, which is plus 15. So on this side we also have 17. So 17 and 17, they balance, and so this is our checked full redox equation. So as usual, let's just check to finish off that we've met our learning objective and see if we are able to apply the electron transfer model of redox to d-block elements. So the electron transfer model is the half equations transferring electrons, and we've applied that to d-block elements. Let's see, we've applied it to zinc and silver, and we've applied it to iron and manganese at least. So I think we've done that. Let's give ourselves a nice red tick. See you in the next lesson.